Hello viewers, today in this part of the lecture we will discuss engineering materials part 3, that is thermal properties of materials, and the outline for this talk is as follows. We will discuss laws of thermodynamics, the concepts of entropy and heat capacity, the concept of specific heat in solids, and what are the models that can be used to understand specific heat of solid. Then finally, we will discuss the contribution of electrons to specific heat of solid. Laws of thermodynamics. Thermodynamics can be explained by three major laws, and they are first, second and third law of thermodynamics. So, the first law of thermodynamics is energy is conserved and both heat and work are form of energy, and if we represent it mathematically, then it is represented as follows, that is du is equal to dq plus dw, where du is the internal energy of the system and dq is heat. If we have given heat to the system, then we call it a positive quantity, and if we have extracted heat from the system, then heat is a negative quantity. Similarly, dw is represented total work in the system, and this value will be positive when work is done on the system and negative when the system works on the environment. Then the next law is second law, which is stated by two different scientists, and both the statements are correct if we look at the statement from the perspective of heat engine. Now, the first statement, which is given by Clausius, goes like this, that is, no process is possible whose sole result is the transfer of heat from a colder body to a hotter body. And the same statement is little bit modified and represented by Kelvin, and which goes like this: no sole process is possible whose sole result is the complete conversion of heat into work. Now, as I said that both the statements are correct if we look at both the statements from the perspective of an heat engine. The third law is again proposed by two different scientists, and the first scientist who proposed the third law is Nernst. He said that near absolute zero, all reaction in a system in internal equilibrium take place in no change in entropy, and the same statement is little bit modified and presented by Planck. He said that the entropy of all systems in internal equilibrium is the same at absolute zero, and this value, which is constant at absolute zero, can be considered as 0. And the consequence of third law of thermodynamics is the unattainability of absolute zero temperature. Now, if we look at the second law of thermodynamics, then we can observe that there is a physical quantity which can be derived from the second law of thermodynamics. So, this physical quantity is called entropy, and we can say that it is the direct consequence of second law of thermodynamics. Now, since dq by t is independent on states, so this particular quantity can be defined by a new parameter called entropy, and this is represented by S. So, entropy S is equal to dq by T. For a reversible system, the total entropy for the system is always 0, but for an irreversible system the total entropy tends to increase, and the best example is our universe, which is where the total entropy of the universe is increasing with time. Now, the next concept that we want to understand is heat capacity, and heat capacity can be defined in the following way. So, it is the amount of heat required to increase the temperature of a body by 1 degree Celsius. So, if we quantify heat capacity by using a particular formula, then we can write heat capacity C is equal to dQ by dt, where dQ is the energy required to get a temperature change of dt, and the unit of heat capacity is joule per mole Kelvin. Now, we understood what is heat capacity. Now, the next concept is specific heat capacity. So, specific heat capacity is basically the heat capacity per unit mass of a substance, and specific heat capacity is represented by small c, that is equal to dQ by m dt, and the unit of specific heat capacity is joule per kilogram Kelvin. The next concept that we want to understand is phonons. Now, in solids, the thermal energy assimilation or the thermal energy that we extract from solids is basically due to the vibration of atoms. Now, these atoms in the solids, they keep on vibrating depending on what is the temperature at which the solid is kept, and these vibrations, they are having a very high frequency and a very low amplitude, and these vibration will have certain specific frequencies, and the associated energy with these frequencies can be quantified with small packets of energy, which is called phonon. So, these waves or these vibrational frequency, if we analyze in the solid, then they form a type of wave which are analogous to elastic waves or kind of sound waves. Now, the atoms in the solids, they are not independently moving. That means, when they move, because they are also attached to the neighboring atoms, when they move, they also keep jiggling the neighboring atoms, and these waves, as I said, they propagate with the velocity of sound, because these are elastic waves, and sound wave is also a form of elastic waves. If you want to understand how the thermal conduction happens in solid, then we need to explain the thermal conduction in solids by using the concepts of phonons. Without that, it is very difficult to understand why and how thermal conduction happens in solids. Now, because whatever basic understanding is required to understand the thermodynamics of a solid, we defined them. Now, if we want to intricately understand the specific heat of solid, then we have to take help of vibrational energy, because they are the energy related to the vibration of atoms, which gives us the phonon concepts. Now, vibrational energy of a crystal of n number of atoms is equivalent to the energy of a system of 3n harmonic oscillators, where n is the number of atoms in the solids. Now, to understand the specific heat of a solid, there are various models which have been proposed by various scientists, and the distinction between the theories is the spectrum at which they are defining the frequency of vibration. So, the main aim of different theories is to find out the different modes of frequency or different modes of vibration and the corresponding wavelength related to that mode of vibration. So, the first theory that can be used to understand the specific heat of solid is the classical theory, which is basically calculating the average energy of harmonic oscillator using classical statistical mechanics. And if we mathematically represent the average energy of the oscillator, then we can represent it in the following way, which is the average E is equal to integration of E into exponential minus E by kT dE divided by integration exponential minus E by kT dE, where E is equal to p square by 2 m plus half m omega square r square. So, for a harmonic oscillator whose mass is m and angular frequency is omega, we can represent the total energy in the above equation, that is E is equal to p square by 2 m plus half m omega square r square. Now, if you calculate the average energy of harmonic oscillator using the above equation, we can find the value as average energy is equal to 3 n kT, and from this we can find out the specific heat, because heat is the first derivative of the average energy with respect to temperature, and which gives us the value 3 n k for n harmonic oscillators in solid. Now, if we look at this equation of specific heat, then we find that it is independent of temperature, which is true for high temperature, but when it comes to low temperature, we cannot match the values with the experimental value. That means, there is some discrepancy, and to resolve this discrepancy, Einstein proposed a model, and he used quantum mechanics to explain the specific heat of solid. So, his assumption was that all the atoms in the solid, they vibrate independently and with a single frequency. So, he used Planck's blackbody radiation expression to explain the specific heat of solid, and Planck gave the expression for energy for blackbody radiation, which is E is equal to n h nu, where n is integer values of 0, 1, 2 and so on, h is Planck's constant and nu is the frequency associated with the quantum of energy. So, using this concept given by Planck, Einstein tried to find out the average energy of the harmonic oscillators, and we know that in quantum mechanics the energy of a harmonic oscillator is represented by the following equation, that is E is equal to n plus half h nu, where n is the integer values. And using this, it was found that the average energy is equal to h nu by 2 plus h nu by exponential h nu by kT minus 1, and the total energy for n number of atoms was E is equal to 3 n into h nu by 2 plus h nu by e to the h nu by kT minus 1, where n is the total number of atoms in the solid. Now, we found out the average energy as well as the total energy for the harmonic oscillator. Now, how to find out the specific heat? As I said that the specific heat is the first derivative of the average energy with respect to temperature. By using this formula, Einstein found that the specific heat at high temperature is as usual independent of temperature, whereas at low temperature the specific heat was varying inversely with temperature. And when we match the theoretical data with the experimental value for specific heat, we found that the values are somewhat close, but still not exactly matching with the experimental value. That means, there is still something missing in the theory. So, to resolve this problems of the value of specific heat of solid at low temperature, Debye proposed a theory. And as per the Debye theory, he assumed that there is a range of frequency of vibration for atoms, and since each atom is coupled to the neighboring atom, so the mode of vibration for each atom cannot be a single frequency, it has to be a range of frequency. And he also defined a higher cutoff frequency of the vibration of atoms, which he called Debye cutoff frequency. So, to find out the number of modes of vibration for the atoms, he wanted to find out the number of modes of vibration for a continuous system. And to do that, he chose a very simple continuous system, that is a string attached at the two ends. And this is a one dimensional system, and he considered the wave equation for this one dimensional system, which can be represented in the following way, that is del square u by del x square is equal to 1 by c square del square u by del t square, which is the wave equation in a one dimensional string. And this satisfies a solution given as follows, that is u x t or u as a function of x and t is equal to a sin n pi x by L into cos 2 pi nu t into t. And from this we can find out the wavelength lambda n is equal to 2L by n, and frequency nu n is equal to c by lambda n or c n by 2L. Now, this is in one dimension. If we extend this particular concept to 3 dimensional solids, then the possible modes of vibration can be represented by the following equation, that is pi square by L square into nx square plus ny square plus nz square is equal to 4 pi square nu square by c square, and after simplification that gives us 4 pi square by lambda square. Here nx, ny, nz are integer values, and we can represent nx square plus ny square plus nz square is equal to r square. So, the above equation can be represented by r square is equal to 4 L square by lambda square or 4 L square nu square by c square. Now, here nx, ny, nz are positive integer value, and we can draw an analogy where we can consider a spherical cell of thickness dr, and we consider nx, ny, nz is the positive values present in the positive quadrant of this spherical cell. And if we want to find out the number of points in the cell of thickness r and r plus dr, it is equal to 1 by 8 4 pi r square dr. So, the number of modes will now become z function of nu dr is equal to 4 pi v by c square into nu square d nu. So, this gives us the number of modes of vibration in a 3 dimensional solid. But Debye consider the waves that are propagating in the solid are of two types, one is longitudinal wave and the other one is transverse wave. So, the Debye cutoff frequency that he calculated can be represented by the two types of wave, which is given as follows. the Debye cutoff frequency is nu dq is equal to 9 n by 4 pi v into 2 by Ctq plus 1 by Clq, where Ct and Cl are transverse and longitudinal velocities. After knowing the Debye cutoff frequency, he used Planck's blackbody radiation expression for energy to find out the energy of the harmonic oscillators, and that is E is equal to integration 0 to nu d z nu h nu by exponential h nu by k t minus 1 d nu. And after solving this equation, it was found that the specific heat for the solid matches exactly in both high as well as low temperatures. And as in the previous two theories, the specific heat was independent of temperature, but at low temperature here the specific heat is proportional to the third order of temperatures, and it matches exactly with the specific heat that is found experimentally for a solid. So, usually it matches well when the temperature is below 0.1 theta d, where theta d is the Debye temperature. Now, this is the specific heat of the solid due to the contribution of the vibration of atom, but vibration of atom is not the only one which contributes to the specific heat of solid. There is also contribution of the electrons in the atoms, though the contribution is less, but when it comes to find out the exact value of specific heat, then we must consider the contribution of electrons as well to find out the accurate value of specific heat of solid. Now, these electrons which also absorb some amount of energy from at a given temperature. So, these can be included in the specific heat calculation of a solid. Though the contribution of electrons towards the specific heat of solid is more prominent in metals, it is very less contribution from the electrons in case of insulators and semiconductors. So, the thermal conductivity or the propagation of thermal heat in solids, if they are insulator or semiconductors, are mostly due to the thermal vibration of the atoms, and we can safely neglect the contribution of electrons in insulators and semiconductors. Whereas, for metals, the predominating factor for thermal conductivity is coming from the electrons. Now, there is also another contribution of electrons towards the specific heat of solid. These are found in a very specific solid or very specific metal, which are magnetic materials. In there, the random distribution of electron spin in ferromagnetic material also needs some amount of energy, and this can be studied when we try to understand the variation of specific heat of these ferromagnetic materials with respect to temperature, and when the temperature goes through the Curie temperature. At that time, we found that in the curve for specific heat with respect to temperature, there is a spike at the Curie temperature, and this particular feature of electron towards the specific heat of solid, or specifically the specific heat of ferromagnetic material, should also be considered when we are interested to find out the specific heat for magnetic materials. in this lecture, so far what we discussed, if we present them in a nutshell, then it can be presented in the following points. That is, we discussed the various laws of thermodynamics, and we found that entropy is the direct consequence of second law of thermodynamics. Then we tried to find out a very important property of solid, that is specific heat of solid, by using different models, and how those models are different from each other. That is what we discussed. And finally, we tried to understand the contribution of electrons towards the specific heat of. We also have discussed the physics of phonons, which is basically originating from the thermal vibration of atoms, and which is one of the very important concept to understand the specific heat of solid. And hope you would have liked the lectures. Thank you.